Hello everyone, welcome to my channel. This is lecture number 5. It is related to diffusion of component A from bulk to the surface of catalyst. So we have discussed the 7 step during heterogeneous catalytic process this in the previous lecture. Suppose this was step number 1, diffusion from bulk to the surface of catalyst. In the second step, intraparticle diffusion. In the third step, adsorption. In fourth step, reaction. In step number 5, desorption of component B of the product, desorption of the product from the surface. In step number 6, the diffusion of product inside the pore, and in step number 7, diffusion from the surface of catalyst to the bulk fluid again. So in this lecture we will discuss about the first step, which is the diffusion of component A from bulk. This is bulk of A, from bulk of A to the surface of catalyst. This is the surface of catalyst. This is the catalyst, and this is the surface of catalyst. This is so diffusion of A through this liquid film around the catalyst. This is a liquid film around the catalyst. So this is the fluid film or liquid film around the catalyst. So diffusion will take place through this liquid film from bulk to the surface of catalyst. So in this lecture we will discuss about diffusion of component A from bulk to the surface of catalyst. So this is bulk fluid. Concentration of A in the bulk is CAB. And this is the liquid film. This is liquid film. This is the catalyst surface. Catalyst surface. Catalyst surface. And so the A will diffuse from the bulk to the surface of the catalyst through this liquid film. This liquid film. This is the liquid film. Liquid film. So the molar flux of component A through this liquid film, which is around the catalyst particle, will be given by minus DAB, diffusivity of component A in the liquid. So suppose if the liquid is water, this is water film, then component B will be water. And suppose component A is oxygen molecule or nitrogen molecule or some other gas, so the component A will be any gas molecule. Molecule is component A, suppose. So diffusion of gas molecule through water, which form this water molecule form this layer, so this will be the component B. Here you can see this is component B, and here is component A. So diffusivity of component molar flux of A in the R direction. Suppose this is the R direction. This is the R direction. This is the R direction. You can also use Z direction, where I am using R direction. So the molar flux of A in the R direction is equal to minus DAB, change in concentration of A divided by change in distance in the R direction. This is R direction. This is R direction. Okay, this is the molar flux of A, and its unit can be obtained. The diffusivity unit is square meter per second. The molar concentration is mole per cubic meter, and this is the length, which is again meter. So it is mole per square meter into second. So it is molar flux of component A through this liquid film. This liquid film. It is given by this equation, which is nothing but Fick's law of diffusion. So the molar flux of A is minus DAB dCA divided by dr, where dr is the thickness of the liquid film around the catalyst. So this liquid film around the catalyst. Dr is nothing but it is the thickness of this layer. Thickness. This thickness is denoted by dr. Okay. So this can be written as minus dCA divided by dr by dAB. The thickness divided by diffusivity is nothing but resistance to the mass transfer. And the molar flux of A can be written as driving force for mass transfer divided by resistance to the mass transfer. So concentration gradient is the driving force for the mass transfer in this case, and the resistance to mass transfer is dr divided by dab. This is the resistance to the mass transfer. So we can write this equation in this form. So driving force, this is the driving force, and this is the resistance to the mass transfer, and it is nothing but it is the molar flux of A in the r direction. So suppose this is the catalyst particle having diameter d1, and this is the liquid film. Suppose liquid film around the catalyst particle. Its thickness is suppose dr1. This is the thickness. This dr1 is the thickness of the liquid film around the catalyst particle. And suppose component A, this is component A, and the velocity of the fluid is suppose it is 1 meter per second. Suppose there is component A. Suppose there is some component A which is diffusing, and it is absorbing on this catalyst surface from this surface. Suppose this is a surface from which the A is diffusing toward this catalyst surface. So here the concentration of A is CAB, suppose bulk, and here the concentration is CAS, concentration at surface of the catalyst. So okay, so the molar flux of component A is DAB dCA divided by dr1. The dr1 is this thickness. This is dr1. This thickness is dr1. So again dCA divided by dr1 divided by dAB. So dr divided by dAB is resistance to mass transfer, and dr1 divided by dAB is r1, which is a resistance number 1 at this condition when the fluid velocity is 1 meter per second. So minus dAB dCA divided by dr2. Now when we increase the velocity of the liquid, then the thickness of the liquid film will decrease. So the liquid film thickness will decrease and it will reach to dr2. This one, the liquid film resistance will thickness will decrease. This is dr2, this thickness. Here this is decreased. So dr2 divided by dab is again a resistance number 2 to the mass transfer. So dr2 divided by dab is resistance number 2 in this case when the velocity of the liquid is 2 meter per second. So as we know that dr divided by dab is a resistance to mass transfer, at velocity when the fluid velocity is 1 meter per second, resistance to the mass transfer will be r1. When the velocity of the fluid is increased, resistance to mass transfer will be r2. So when we increase the velocity of the liquid, the thickness of the liquid film will decrease. So when the thickness of the liquid film is decreased, then resistance to mass transfer will also decrease. So this r2 will be decreased. S will be small as compared to r1. So flux in r direction of component A will be written as dCA dr1 divided by dAB. And for case number 2, when the velocity of liquid is 2 meter per second, then resistance to mass transfer will be this one. So now this is resistance to mass transfer, and the reciprocal to the resistance of mass to the mass transfer. The reciprocal of resistance is nothing but it is the mass transfer coefficient. So the reciprocal of resistance to the mass transfer is nothing but mass transfer. This is the resistance to mass transfer. Reciprocal to the resistance to the mass transfer, reciprocal of the mass transfer resistance is nothing but the mass transfer coefficient. So this is the mass transfer coefficient. Now, so when we increase the velocity of the fluid, when we increase the velocity of the liquid, suppose it decrease the film thickness, the liquid film thickness will decrease, and hence decrease resistance to the mass transfer. So when we increase the velocity of the liquid, the stagnant film thickness will decrease, and hence the mass transfer rate will increase. So when resistance to mass transfer decrease, molar flux, and hence the mass transfer rate will also increase. So when resistance to mass transfer decrease, the molar flux will increase, and when the molar flux increase, the mass transfer rate will also increase. So here you can see this is the change in concentration. This is resistance to mass transfer, and here the reciprocal to the reciprocal of resistance is nothing but it is the mass transfer coefficient. So in this case you can see that this is the mass transfer coefficient, and this is change in concentration for case number 1 when velocity of the liquid is 1 meter per second, and when velocity of liquid is 2 meter per second, then mass transfer coefficient will be K2. So K2 is greater than K1. So when we increase the mass transfer, when we increase the velocity of the liquid film thickness will, the stagnant liquid film thickness will decrease, and hence mass transfer rate will increase. Now this was step number 1. Now we will discuss step number 2, which is internal diffusion. So this is the again component A. This is the bulk of concentration of A in the bulk region, and this is the catalyst, surface of catalyst, and here the concentration of component A is CAS. This is the liquid film thickness, and this is the pore and catalyst, the pore of catalyst. Okay, now the rate for mass transfer will be equal to K and CAS and CAI. So CA is the concentration of component A in this inside the pore. So here the concentration of A will be CAI, and the concentration of A at this surface of catalyst, this is the surface of catalyst, this. So here the concentration will be CAS. So the rate will be equal to K mass transfer coefficient CAS minus CAI. But in many cases, the concentration here, the concentration of A in this place is very small, because A is converting into B on this surface. So the concentration of A is, so in most cases it is very small. So we will neglect this one. So the rate will be equal to K and CAS. Now as the particle size increases, resistance to the mass transfer will increase. It will take long time for molecule to react. So when we increase the size of the particle, the resistance to mass transfer will increase, and it will take long time for molecule to react with surface as well as inside this particle in these places. So similarly, when the particle size decreases, internal diffusion will not limit the reaction. Less time will take place. So when the particle size, when we decrease the particle size of catalyst, then the reaction time will decrease. The molecule will take less time inside the catalyst pore when we decrease the particle size. But when we increase the particle size of the catalyst, the molecule will take long time to react, to absorb on the inside surface of the pore of catalyst. So this was all about the internal diffusion and the diffusion of component A through the to the stagnant liquid film around the catalyst. So here you can see a graph when the particle diameter, when diameter of catalyst is increases, then internal diffusion will be slow. Internal diffusion will slow, because when we increase the particle, suppose this is the small diameter particle and this is large diameter particle. So here you can see in this for the molecule will take large time to react, to absorb and desorb from the surfaces. But in this small particle, the molecule will take very less time to absorb and react. So here you can see the in large diameter particle, when diameter of the particle is increases, the mass transfer, the internal diffusion will limited the overall rate of reaction. So internal diffusion will slow when we increase the diameter of the catalyst particle. But when the diameter of the catalyst particle is decreases, then the surface reaction will be slow. Surface reaction will be slow, and this is the Kr, rate constant. So this was all about surface reaction, that how molecule react and how molecule transfer from bulk region to the surface of catalyst. Thank you very much for your attention. In the coming lecture, we will discuss about the adsorption isotherm. Thank you very much for your attention.